Okay, the second example I want to do for chapter 7 is a little bit long, so I just broke it into its own movie here. So it's similar to what we've done before, where the first example was an Atwood machine, but just two pulleys or two masses connected over a pulley. Now we have one mass sitting on a table here, connected to another one that's hanging over the edge of the table. And if we let this go, and if mass B is big enough, the system will start to accelerate downward. Okay, so we are given some information here. So we know mass A is 1 kilogram. We know mass B is 0.5 kilogram. And we know the coefficient of static or kinetic friction is 0.1. And then we want to find the acceleration and the tension. Okay, and I'm just going to sketch it quick on my paper, and then we'll go to the camera. So A is on the table, connected to a pulley here. B is hanging below. Okay, switch to our camera. All right, so that's where we are so far, and this is going to accelerate this way, and this will accelerate this way. So our coordinate system is going to be different for these two masses, right? So we want positive to be in the direction of acceleration, so let's say that's our plus y for mass B. And then for A, we can say, again, this is our positive x, that's the direction of acceleration, and plus y. Okay. And so our motion diagram is going to look like, we can just do for A, let's say, where it's going to be accelerating. So our dots get bigger and bigger. And then we can do our free body diagram. And our free body diagram could be. Okay, so let's look at B first. It is going to have force of gravity. Force of gravity on B. And there's going to be tension opposing that, but force of gravity on B is going to be bigger, right? So that we get an acceleration downward. Okay, so now here we are on A. So we have that same tension now is pulling A to the right, right? So this is the force of A pulling back on B. This is the force of B pulling on A. So that's our tension. Now force of gravity should be a little bigger because this is a bigger mass. FG, I'm not going to do twice as big because I'm just going to run out of room. And there's my normal. Let's say it should be the same as gravity, same length, opposite direction because we're not accelerating. And then we have some force of friction resisting, but that should be less than the tension that's pulling to the right. Okay, so we still get an acceleration. And again, we're just going to put as a reminder, my coordinate axes there. And I'm going to say y is down, plus y is down, and x can be over there. All right, so now we go on to our second law, right? So we're going to do sum of the forces. Let's just say this is going to be MA over here. We'll do this one first. Sum of the forces is MA times acceleration. Again, we're going to just do our column vectors, write out the vectors, and then we'll do column vectors, right? So we're not worried about directions yet. We're just putting the vectors down, right? So we have tension, we have force of friction, we have the normal, and we have the force of gravity, and those are going to sum up to give us some acceleration. Okay, now we can go to column vectors. And tension, so again, remember this is our x and our y, so top row is x, bottom row is y. So tension is in the plus x direction, so it's positive, and it has nothing in the y. Friction is in the negative x, and nothing in the y. Force of the normal is 0 in the x and positive in the y. And then force of gravity is 0 in the x and negative. And I'm just going to swap now right into MAG. Right, that's the force of gravity. And that equals MAX, MAAY. Okay, and this is, no, that's what we're trying to find. Y is 0. Okay, so in the x equation, if we bring that out here, we have tension minus the force of friction equals MA times our acceleration. And then in the y direction, we have force of normal minus MAG equals 0. So this tells us our normal in this case is MAG. Friction we can rewrite as mu times the force of the normal. So tension minus mu times force of the normal equals MAA. And then we just found from our y equation what the normal is, so we can plug that in. So we have tension minus mu MAG, right? That's our expression for the normal, equals MAA. And we're going to have to eliminate what, we have two unknowns here with tension and MA. So I'm just going to finish this off and rewrite it in terms of tension by itself. So MAA plus mu mass of A times acceleration of gravity. Okay, and then let's look over here and we will do the sum of the forces on B equals MB times acceleration. So just our vectors, we have tension and we have the force of gravity on B, and that equals MBA. And then we'll do our column vectors just to get practice here. So it's our X and our Y. Tension has nothing in the X. And again, for mass B, I'm saying positive is downward. So now tension is negative. Okay. And then the force of gravity has nothing in the X, and it is in the positive direction, so we're going to do MBG positive, and then that equals MB and X and MB AY. Okay, so that one is 0. Okay, and this is our system acceleration, right? This is the same as, not cross that out there. And X, so that's the same, these are the same accelerations, we're just going to call them A from here on out. Okay, so this equation gives us negative tension plus MBG equals MBA. So now this is our second equation that we have here, right? So we can take our tension that we solved for here and plug it into this equation. So we get negative MAA plus mu MAG plus MBG equals MBA. Okay, and now we can solve for acceleration, so let's group that over to the other side. So we have, well, let me just factor in the negative first. So mass of A times acceleration minus mu mass of A times acceleration of gravity plus mass of B times acceleration of gravity equals mass of B times acceleration. I'm going to move this one over. So I'll get MBG minus mu MAG equals mass of A times acceleration plus mass of B times acceleration. And then I can factor that out to A. And I can factor out a G on this side, or just leave it because I kind of like how it shows us what the forces are doing. Okay, and now let's solve for A. So we get the acceleration is the mass of B times acceleration of gravity minus mu times the mass of A times acceleration of gravity divided by the combined mass MA plus MB. So again, let's look at that, right? So our relationship, right, is that acceleration is the net force over the mass, okay? So again, if we think about, instead of looking at these two blocks individually, we can think about them as a system, right, of two blocks. The force that's driving in the direction of motion is the weight of block B. The force that's resisting that motion is the friction on block A. So now let's look at what our acceleration says. We have the force of gravity on B. That's in the direction of acceleration, and it's being opposed by the force of friction. Force of gravity on B being opposed by the force of friction on A. And then it's dividing by the system mass. Okay, so that's a different way of looking at it that actually eliminates having to do the analysis of each mass individually. If we group it as a system, think about one force trying to move it down in the direction of acceleration, the force of friction here, trying to resist it. And then we actually can ignore the impact of, the tension. It ends up not being important. Okay, so if I plug in my numbers, you guys can try and do that as well. I get that the acceleration is 2.61, but definitely check me. I've been known to make mistakes before. And then I can come back over here, plug in A, and solve for tension. And I got 3.59 newtons. Again, check me. Extra credit if you find a mistake. Hope you enjoyed that. It's beautiful, isn't it? Okay.